No, don't take that. All right. That front cover. Take a look at the front cover. So unfortunately, because I'm putting this together as we go, this package contains 5.6. Yes, which is like the AP extras. Everything that we have done up till this point is part of the regular Chemistry 12 curriculum. Okay? This part here, 5.6, is the only extra bit. Okay? There's something else later on with the KEQ, but we need to do equilibrium first. We can't do it yet. But you'll notice I haven't gotten to corrosion because I felt that you guys could learn that from Mr. Colger over the holidays. Okay, because it's not too difficult and he's got some good videos on it. All right? You'll also notice that 5.3D, I haven't made that yet, so there's not going to be, the pages are not going to be in order, so I apologize for that. There's going to be like sections that are just out of order. Maybe I won't even number them, okay? Like, it's just not a lovely thing, and I apologize for that. But anyway, there we are. Shall we carry on then with quantitative aspects of electroplating? You might be asked, how are we feeling about electroplating, by the way? Ish? Yeah? Okay, we can come back to it later if we're still feeling Okay, we can talk about it later, but I do want to get through this today. You might be asked to determine the amount of metal that is plated onto a cathode in a given amount of time. In order to do this, you need to be able to use your AP data sheet. That should have a T at the end. And you should know some basic electrical concepts that I will review with you in case you've forgotten them and haven't seen them since grade 9, which is possible, depending on your physics. And you have to be able to do conversions. We're back doing conversions again. Woo! So on your AP data sheet, it is in the section called Thermodynamics and Electrochemistry. And for this worksheet in particular, we are looking at this formula here. I equals Q over T. Do you guys remember what I is? Current. Do you remember what Q is? Charge. Do you remember what T is? Time. Excellent. Okay. So you're going to need to know that. And if you forget, guess what? Over on the right-hand side, they are defined for you. I is current, Q is charge, and T is time. It gives you the units, amperes, coulombs, and seconds. It does not give you their abbreviations. What is the abbreviation for ampere? A, coulomb, capital C, and obviously seconds is lowercase s, okay? And there's one new thing. I don't know if you come across this in physics at all. Has anyone come across Faraday's constant? No, okay, maybe not, because it sounds like more of a chemistry thing, because it is the charge per mole of electrons, and moles is a very chemistry kind of thing, yes? Okay. So, the electrical concepts. Charge is measured in Coulomb. A Coulomb is the amount of charge in 6.24 times 10 to the 18 electrons. Do you need to know that number? No, okay? It's just there so that you're not like, what? How many? Yeah, it's a big number. A Coulomb is a lot of electrons. If you've had me for grade 9, I said it was a bucket of electrons, okay? Current measures the amount of charge, Q, measured in coulombs, that flows past a point in a second. Yes? So you have I equals Q over T. If you plug in your units for that, you get 1 ampere is 1 coulomb per second. And guess what we have here? We now have 1 coulomb per second is going to be a conversion factor between coulombs and seconds. So if I gave you 2.5 amperes, that would be 2.5 coulombs per second, yes? And you can use that to convert between coulombs and seconds. Faraday's constant, we can derive it. It is the amount of charge on a mole of electrons. So if we said, well, how many electrons is a mole of electrons? Well, that's 6.02 times 10 to the 23 electrons, yes? And a coulomb is 6.24 times 10 to the positive 18. And so there are 96,500, okay, so 96,500 coulombs per 1 mole. Do you need to memorize that number? No, because guess what? It is given to you in great detail to 5 significant figures. Why 5? I don't know, but it's given to you right here. Okay, the key thing is to remember that this can be used as a conversion factor between coulombs and moles. Okay? So, you have these worked answers on here. I'm just going to work through it like writing it. Yes? If we have a current of 2.50 amps and we run it through a solution of iron 3 chloride, okay, I'm just going to write my ions so I have them there. What mass of iron would plate out? And I ran it for 15 minutes. Yes? So the first thing I'm going to do is I'm going to rewrite 2.50 amps. What will I rewrite it as? 2.50, what is an ampere? It is a coulomb per second. I'm going to rewrite that so that I know I can convert between coulombs and seconds. Second thing I'm going to do is I need to have a balanced half reaction. So who is reacting? Who is the thing that's reacting that I'm interested in? Iron, yes, it's turning from iron 3 plus and it's being plated as iron solid, yes? So our half reaction would be going from iron 3 plus to iron solid. What do we have to do to balance that? Add 3 electrons. So now we have a mole ratio between iron and the number of electrons, yes? There are 3 moles of electrons used for every 1 mole of iron produced. Yes? Nothing really new about this, it's just we haven't done a mole ratio with electrons before. Okay, but now we are, because we can do that using a half reaction. The third thing to do is just to do the conversion. Because this is the first one we're doing, we're going to do a map. Okay, what do you think we are starting with? There's only 2 numbers and one of them is a conversion factor. We're starting with 15 minutes. So we're going to start with 15 minutes. What do we want to finish with? We want to finish with grams of iron solid. What steps do we have to do to get from minutes to grams? You can work both ways. What could I convert minutes into? Seconds. Okay, so good, good. What could I convert from to get to grams? Moles. Okay, okay. Moles of Fe. Is there something I could convert seconds into? Look, I can convert seconds into coulombs. seconds into coulombs. And remember, we just learned Faraday's constant. Okay, so it might be worthwhile if you've got a question like this, writing down that 1 Faraday is 96,485 coulombs per mole of electrons, because now you can say, oh, I can go from coulombs to moles of electrons. And from my balanced equation, I can go from moles of electrons to moles of iron, and then to grams of iron. So that's basically how you put it together. So just remember, write out your amperes as coulombs per second. Maybe even write out the Faraday's constant so that you know that it's there for you as a conversion factor. Yes? And then you just do this conversion. So what would that look like? We would have how many grams of iron? We don't know. But we're starting with 15 minutes. We know that there are 60 seconds per minute. We know that there are, and we have 2.50 coulombs per second, 2.50 coulombs per second. We can convert coulombs into moles of electrons. This is kind of the special new part that, you know, this one and the coulombs per second, those are our new conversion factors for this section, okay? So we can say, okay, I have 1 mole of electrons for 96,485 coulombs. And then the molar mass of iron is what? 55? Grams per mole. Did I skip a step? Uh-oh, 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 uh-oh. I went from moles of electrons to grams of iron. Yeah, no, I did skip a step. We need to go from moles of electrons to moles of iron, and there are 3 moles of electrons for 1 mole of iron. And then finally, now we're finally going to convert from moles of iron to grams of iron, and that is 55.85 grams per mole. Yes? So, hard or easy? Easy, as long as you remember that current can be used as a conversion factor. And what's our other new conversion factor? Faraday's constant. And it is given to you in the data booklet, so you don't need to be like, oh no, I can't remember it. It is there for you. Okay? Do you want to go through the other examples? Yes. Okay. All right. So here we have the next example. An electrolytic cell is constructed in which the electrodes are placed into an aqueous solution of copper sulfate. So we have copper ions and we have sulfate ions. I'm probably going to be interested in the copper because I am talking about electroplating. Yes? You can't plate sulfate ions. That just doesn't make any sense. Yes? A current of 3 amps is applied. What should I do with my current? I should convert it to coulombs per second. While I'm at it, what else should I write down? 96,485. I had to type that a lot this morning. Coulombs per what? Mole of electrons. How long? What does it mean when it says how long? Time. And because it is not specified, you might as well do seconds because then you have to do less converting. Yes? And we know that we have the mass of copper, which is 5.00 grams. So, what else do I need in order to complete this question? I need the balanced half reaction. Who are the species going to be in my half reaction? Tell your partner. Who are they? Copper 2 plus and copper solid. Yes? Because we got copper 2 plus and we are plating on copper solid. So copper 2 plus, copper solid. Okay, and that gives us a ratio of 2 moles of electrons for every 1 mole of copper. And we want to know our time, that's what we don't know. So how many seconds is, what are we starting with? Grams, 5.00 grams of what? Grams of copper. What's our first conversion? Grams to moles. What's our next conversion? Tell your partner. Moles of copper to moles of electrons. Yes. Okay, grams, grams, moles, moles. I made that too big. What will we convert our moles of electrons into? Coulombs, yes? There we go. So I want to cancel moles of electrons and find coulombs. 96,485 coulombs for 1 mole. And finally, what's our last thing? Coulombs per second. So that's going to be, let's see. Oh, coulombs need to go down here. Seconds need to go up here. So that's 3.00 coulombs per second. And we get 5 divided by 63.55 times 2 times 96485 divided by 3 is 50, 60.8, 50, 60.8 seconds. How many sig figs? 4? 3, because we only got 3 there, so that is going to become 5060 seconds. Yes? Did I put 4 in the answer that I wrote there? Maybe I did. Let's see. Oh, yeah, I did. That should be 5060. Sorry. Did we want to do the last one? The last one is a little bit different because it's going to ask how much current. How much current? So we want to know I, which is Q over T. And what do we know? We know 10.8 grams of silver. We know 5 hours. So do we know the time? Yes, we're just going to have to convert that into seconds. Wouldn't it be nice if we could convert grams into charge? What is charge measured in? Coulombs. Can we convert grams into coulombs? Well, we better hope so. Yes, we will be able to. Okay, this question would not work if we couldn't. Do you want to do this the longer way or the shorter way? Shorter way? Okay. I equals Q over T, which is equal to coulombs per second, and we don't know how many. Yes? And we're going to start with 10.8 grams of silver over 5 hours. Yes, because we're going to take our grams and convert it to coulombs. We're going to take our hours and convert it to seconds. Do you guys know how to convert from hours to seconds in one step? 3,600. Okay, so we have 1 hour. I made that way too big. Per 3,600 seconds. Great, now I have grams per second. I'm partway there. What do I need to do next? Grams of silver, moles of silver. And 107.9. I know that's not the one in the AP book, but that's okay. It's going to be close enough because I only have 3 sig figs, so 4 sig figs should do me quite nicely. And I happen to know that one by heart. Oh, grams of Ag are gone. Grams of Ag. There we go. That's better. Gag. Okay. What are we going to convert moles of silver into? Uh-oh, what did I forget to do? I forgot to do my balanced half reaction. What is my balanced half reaction? It's going to involve what substance? Silver. So we were looking at silver. We're always going to have the ion going to the solid because it's always going to be involved in electroplating, yes? Oh, it's 1 to 1. Isn't that nice? Yes? 1 mole of electrons per 1 mole of silver. And then finally, we can go Faraday, Faraday, Faraday. We're going to cancel moles of electrons and find coulombs. Why did I write plus? It doesn't matter. Silver and silver plus are identical for all purposes here. But anyway, better to stay consistent. 96 for 85 coulombs. And so we would do the math on that, and we would get, I'm going to cheat this time, 0.537. And if we look at our units, what we have left is seconds and coulombs. So that is coulombs per second, which is the same as 0.537 amps. And I don't think they would mark it incorrect if you had coulombs per second, but I think it's better practice to change it into amps. Is good? You guys ready for 5.6b? Okay. Honest to God, this is a pretty easy section. It's got a big name, Gibbs free energy. We have not talked about it yet because we have not done equilibrium. So, you're not going to understand Gibbs free energy at this point. You okay with that? You are going to be able to plug and chug. Yes? Yes. And you need to know 2 things. We will actually go into Gibbs free energy later, but not today. The key equation is this. It is on your data booklet. So if we go to our second page here somewhere, second page, oh, there it is. Look at this. We have, where is it? On the left. Delta G is equal to negative NFE, where F is, what is F? Faraday's constant, which we just learned about, right? What is N? Number of moles of electrons, okay? Number of moles of electrons. And that makes sense, right? Because we're dealing with electrons. And what is E naught? It's the cell potential. What's it measured in? Volts, okay? So going back, the other thing you need to know about Gibbs free energy, other than the fact that you just need to plug in moles of electrons, Faraday's constant, and the cell potential, is that if delta G is positive, that means that E naught of the cell is negative. Does that make sense? There's a negative sign there, which means that they're going to be inversely proportional to one another. Yes? And if E naught of the cell is negative, that means it is non-spontaneous. We already knew that, yes? So if delta G is positive, the reaction is non-spontaneous. If delta G is negative, then E naught of the cell is going to be positive, and the reaction is going to be spontaneous. We will be dealing with delta G in contexts that are not electrochemical in nature later on. So it is important to know that if delta G is positive, it's non-spontaneous. If it is negative, it is spontaneous. To help you remember that, you can remember that Gibbs free energy is actually related to, but not equal to, potential energy. If you have a change in potential energy from low to high, is that a spontaneous process or a non-spontaneous process? You're lifting something from a low potential and moving it up to a higher potential. Is that spontaneous or non-spontaneous? Non-spontaneous. And you can see that if we have our little hill here, right? If we have to, did I not put the ball rolling up the hill? I meant to have the ball rolling up the hill as well, but apparently I did not get around to that. That's okay. So here's delta G. This is spontaneous. We're going from high potential energy to low potential energy. So the change in potential energy is negative, yes? And that means it is spontaneous. And delta G works the same way. And I meant to have, like, do we need to draw the hill with the ball going up? Would we like that? Do you care? No? Okay. I'm going to draw it down here. It'll make me feel better. I meant to have it on here. So if we have a ball, and it's going up the hill, we are going from low potential energy to high potential energy. So our change in potential energy is positive, and that is obviously, the ball will not roll up the hill on its own. You will need to put in energy to make it happen, so that is non-spontaneous. And delta G works the same way. Delta G is more complicated. It actually involves not only potential energy in terms of its enthalpy, but it also involves the temperature of the system and the entropy of the system. Do you guys know about entropy? No. Okay, we'll learn about that later. It's basically the randomness of the system, but we'll deal with that later. Okay. So what do we need to know about this? Well, we need to be able to plug things into that formula, chug them through, and then decide if delta G is negative, the reaction is spontaneous. If it's positive, it is non-spontaneous. What else do we need to know? Well, we still need to know about charge, which we just talked about, so we're not going to do that again. We need to know, in this case, about volts. Okay? What is a volt? A volt is the amount of energy per Coulomb of charge. So how much energy is held in a Coulomb of electrons? Okay? So we have if there's 1 volt, it is 1 joule per Coulomb. And again, guess what this can be used as? A conversion factor. So you need to know that a volt is a joule per Coulomb. And this is not really given to you. But is it given to you? Yes, it is. Ooh, look. Hang on, where did it go? This one actually is given to you here. A volt is 1 joule per Coulomb. So that one you don't even have to remember or plug things in or whatever. Okay? So that's nice. We still have Faraday's constant, which we can use as a conversion factor if we need to. Or, in this case, we probably won't use it as a conversion factor. We'll just use it in the formula with the F. Okay? So, here we have nickel and lead reacting together. And you can look up the two half reactions and you can find their reduction potentials. Yes? Would you be able to find the potential of this cell, the E0 cell? Who would be getting reduced? Well, we're told that the reaction goes this way, so what's happening to the lead? Lead's going from 2 plus to 0, so lead is being reduced. We can't guarantee that we're going to have a spontaneous process because maybe they're having us look at a non-spontaneous process. You just have to look at what's actually happening here. Nickel is being oxidized. Okay, and so we have lead is being reduced, so we're going to just use that value right there. Nickel, it's going to depend which version of the formula you like, whether you're going to leave it as negative 0.26 or whether you're going to change it to positive 0.26. So, lead is easy because we just leave it alone because it's reduction. Do you know which version of the formula you prefer? If you don't, you need to come up with one that you prefer so you can use it consistently. Yes? The one thing you don't want to do is be using one time and one the other time and then getting mixed up between the two and then end up subtracting a reduction potential, or sorry, subtracting an oxidation potential, or adding a reduction potential. Like that would just be bad. Anywho, we didn't get through it, but there's really not much to it. You just take your formula, you found your E0 cell, you plug in F, and there's 2 moles of electrons being transferred, and you know that the voltage is that many joules per Coulomb, and you get your delta G. And that's it. So your homework is going to be to do, there's 4 questions on 5.6a, and you can do the 1 question in 5.6b. Okay? See how good you are. See if you can do this one in 9 minutes. That's how long you get for a 4-point question in the written response on the AP exam. And if you can't do it, don't worry. We're not there yet. It's posted on Teams, so if you didn't catch that, everything's posted there. Should be anyway. Yeah, it's time. Uh-huh.